Hello everyone, myself Pranjal Sharma. This is the continuation of my previous video, that is introductory lectures on scalars and vectors. Today we will focus on the analytical methods of vector addition. Before doing that, we have to learn the how to express vectors in terms of component, and also we will learn different vector product methods using its components. Before proceeding to videos to this lecture, I have a request for the new viewers that please watch my previous video, because I have discussed various vital concepts of vectors in that video. After watching that video, you will understand this video properly. Thank you. Let's proceed. So, before going to analytical methods of vector addition, we have to understand the expression of vectors in terms of components. For this, we have to learn a new concept known as resolution of vector. Resolution of vectors. Resolution of vectors means resolving or splitting the vectors into components along the axis of the respective frame. That means if we consider a vector in two-dimensional plane, let xy be the plane where A is a vector. So A has a component along x direction, which can be written as ax, and it has a component along y direction, ay. So any vector A in two-dimensional plane can be written as ax plus ay. Again, we know that any vector A can be written as its magnitude with the product of unit vector. Here n can be the unit vector. This is unit vector, and the direction of this unit vector is similar to the direction of A. Please, for the unit vectors, please watch my previous video. Now, in this similar way, we can express ax as modulus of ax or magnitude of ax into here the unit vector. Since the ax is in the direction of x axis, so the unit vector in this case is I cap. And similarly, ay can be written like this. So the vector A can be now written as xi magnitude of ayj, or simply axi plus ayj. So this is the two-dimensional expression of vectors in terms of its components. Now we can calculate this ax and ay. If we draw a vector parallel to ay with the same magnitude like this, then this vector and this vector have the same direction and magnitude. Therefore, this vector is equal to ay. So we can write it as ay vector. Let theta be the angle made by A along the x direction. So by applying simple trigonometric formula, we can calculate sine, cosine and tangent values. So here cos theta equal to we know that base by hypotenuse. Here base is ax and hypotenuse is a. So ax is equal to A cos theta. Similarly, sin theta equal to perpendicular by hypotenuse. Here perpendicular is AY and hypotenuse is A. So AY equal to A sin theta. And if you want to calculate the value of theta, then we know that tan theta equal to P by B, that is perpendicular by base. That means AY, here perpendicular is AY and base is AX. And theta equal to tan inverse of AY by AX. By putting the value of AX and AY in here, the vector A can be written as A cos theta I plus A sin theta J. So this is the two-dimensional expression of vector A in terms of its components. Similarly, we can express a vector in three-dimensional space. In three-dimensional space, X, Y and Z, let A be a vector. So it has component along AX, component along x-axis, which is AX. AX has a component along y-axis, which is AY, and component along z-axis, which is AZ. So any vector A in three-dimensional form can be written as AXI plus AYJ plus AZK. Let A makes an angle alpha with x-axis, angle between y-axis and A be beta, and angle between z-axis and A be gamma. Then vector A can be written as A cos alpha I plus A cos beta J plus A cos gamma K. Here cos alpha, cos beta and cos gamma are known as direction cosine. Now, what is direction cosine? Direction cosine means how the vector bend or lean towards that particular axis. Here, cos alpha means the how a vector lean towards the x-axis. A cos beta, here cos beta gives how the a vector lean towards y-axis. Similarly, for cos gamma, it is how the a vector lean towards z-axis. Actually, or we can say that direction of cosine gives the projection of vector in that particular direction or particular axis. That means cos alpha gives the projection of A along x, cos beta gives the projection of A along y, and cos gamma gives the projection of A along z direction. So we have learned how a vector can be written into its components. In this way, we can write any vector. Suppose R be a position vector. So what is position vector? Please see my previous video. Let R be a position vector. So R has this component along x direction. It is x. Has its components along y direction, which is y. Has a component along z direction, which is z. So R can be written as xi plus yj plus zk. Now we learn about the vector addition, that is the analytical representation of vector addition. In my previous video, I have explained how we can add two vectors graphically. Now we learn how two vectors can be added analytically. Vector addition and analytical method. Let A and B are two vectors. So A can be expressed as its component like this. Similarly, B can also be represented to its components now. A plus B, the vector addition can be calculated as follows. Here A, AXI plus AYJ plus AZK plus B means BXI, BYJ, BZK. So here we will add X component of A with X component of B. AX plus BX I. Similarly, we can add Y component of A with Y component of B, and Z component of A and Z component of B. Okay, in this way we can add two vectors. Similarly, we can subtract two vectors. Subtraction. Here A minus of B is equal to AXI plus AYJ plus AZK minus BXI, BYJ, BZK. Now again we subtract B, X component of B from X component of A. That means AX minus of BX I, AY minus of BY, Z cap, AZ minus of BZ K cap. In this way we can also subtract two vectors. So we have learned how we add two vectors or subtract two vectors analytically. Now we will learn multiplication of two vectors using its component forms. In my previous video, I have already told that there are two types of vector product. One is dot product, another is cross product. Dot product is also known as scalar product, and the cross product is also known as vector product. Why the dot product is known as scalar product? Because the product of two vectors in dot product, the product of two vectors give a scalar quantity. Now let vector multiplication. Let A and B are two vectors. So A can be written as AXI plus AYJ plus AZK. Similarly, B can be written as BXI plus BYJ plus BZK. So here A dot B, that is dot product. A dot B is the dot product. Now AXI, sorry, AYJ, AZK dot BXI, BYJ, BZK. Now AX AXI dot BXI, BYJ, BZK plus AYJ dot BXI, BYJ plus BZK plus AZK, K cap dot BXI, BYJ, BZK. So AX BX I dot I plus AX BY I dot J plus AX BZ I dot K plus AY BX Z dot I, AY BY Z dot J plus AY BZ Z dot K plus AZ BX K dot I, AZ BY K dot J plus AZ BZ K dot K. Now in my previous video I have given the definition of dot product. Any two vectors are in dot product can be written as A dot B equal to magnitude of A, magnitude of B, cos of theta, where theta be the angle between A and B. Since there is no vector term present in the right hand side, that means the product of two vector is a scalar quantity in the product. Therefore, it is also known as scalar product. So here, if we observe in this expression, then we found that different kinds of vector products of unit vectors. Here, let's check first two dot product of two identical unit vectors. Let's I dot I equal to, similarly here modulus of I, the unit vector along x direction. Again this is also I, so unit vector along x direction. And here, since these two vectors are direct along the same direction, therefore the angle between them is 0. So the cos of 0. Now we know that any unit vector have unit magnitude, that means 1. So modulus of I equal to 1, modulus of 1 equal to I equal to 1, and cos 0 is also equal to 1. That means I dot I equal to 1. Similarly, we found that J dot J and K dot K equal to 1. That means product of identical unit vectors, dot product of identical unit vectors have value 1. Now let's check product of two different unit vectors. Let's I dot j. Here again from the definition, modulus of I, modulus of j, and cos of, here I and j are the unit vectors along x and y direction, therefore they are mutually perpendicular to each other. So the angle between them is 90 degree, and we know that cos 90 equal to 0. So the product is 0. That means two different unit vectors dot product is always 0. Two perpendicular unit vectors dot product is always 0. So that means all the terms will vanish, only this term and this term will retain. The final expression here, ax bx I dot I equal to 1. So I dot j equal to 0, I dot k equal to 0, j dot I equal to 0, and j dot j is equal to 1. So this is ay by. Again as j dot k equal to 0, k dot I equal to 0, k dot j equal to 0, and k dot k equal to 1. So az bz. So two vectors in component form have a scalar product in this form. Now we will do the cross product using components of vectors. Now a and b are two vectors. A can be again written as axi plus ayj plus az k bxi byj bz k. So a cross b here is axi plus ayj plus azk cross bxi byj bzk, or axi cross of all bxi byj bzk plus ayj cross bxi plus byj plus bzk plus azi cross bxi byj plus bzk, or here ax bx and this I will product with I. So x bx I cross of I, ax by I cross of j, ax bz I cross of k. So this is the plus sign here, plus again ay bx j cross of I ay by j cross of j plus ay bz j cross of k plus az dx I cross of k cross this is k, sorry. So k cross of I plus az AZ BY, K cross of J plus AZ BZ, K cross of K. Okay. In my previous lecture, I have defined the cross product of two vectors. Suppose A and B are two vectors. A and B are two vectors, then their cross product can be written as modulus of A or magnitude of A, magnitude of B, sine of the angle between them, and the unit vector which is perpendicular to the plane in which A and B lies. That means this unit vector is perpendicular to both A and B. Since the right hand side of is contain a vector, that means the cross product of two vector gives a vector quantity. Therefore, cross product is also known as vector product. Now, by using this definition, we need to calculate the cross product of unit vectors. So, at first, we need to calculate the cross product of two identical unit vectors. Let I cross I. Here, from the definition, the modulus of I, in place of B we write modulus of I here because both are identical. Since they are identical, not only in terms of magnitude but also in the direction, that means both are in the x direction, so their angle is 0, and this is n cap. So n cap here is actually, so here sine 0 equal to this value is equal to 0. So result is what? It is 0. So any two identical vectors, the cross product of any two identical vector always be 0. So even in case of unit vectors, it is possible, it is applicable. So J cross J and K cross K is equal to 0 because the angle between them is 0 degree. They are in the same direction. Now, if we want to calculate a cross product between two different unit vectors, say I cross J. Here from, again, this is modulus of I or magnitude of I, and this is J, and the angle between them is 90 degree because I is in the direction of x axis, J is in the direction of y axis, and we know that x and y are perpendicular to each other, therefore their vectors are perpendicular to each other. So I, J, and their angle is 90 degree. And here the unit vector is perpendicular to both I and J, and we know that the perpendicular vector of I and J is K. So it is K cap. Now if you want to calculate the product, then it is 1. This is also 1. And sine 90 is equal to 1 and K cap. So the result is I cross J equal to K cap. Similarly, you will find J cross K equal to I and K cross I equal to J. And always remember one fact, that the cross product is not commutative. That means a cross product of two vectors A cross B is not equal to B cross of B. Actually, it is equal to minus of B cross of B. So by using this identity, we can calculate I cross J equal to K. So thus J cross K equal to, J cross of I. J cross of I equal to, I cross J equal to K, J cross of I equal to minus of K. J cross K equal to I, so K cross of J equal to minus of I. And k cross of I equal to j, so I cross of j equal to k. I cross of k equal to minus of j. Okay. So these are actually depends on the direction of the product of unit vector. So you have to remember it by using a beautiful trick like this. Suppose I, j, k are 3 unit vectors. Then if you obtain cross product along the clockwise direction, that is I cross j, if you I cross j give k, j cross k give I, k cross I give j. If you calculate the cross product in anti-clockwise direction, that means I cross k give minus of j, k cross j give minus of I, and j cross I give minus of k. So in this way you can remember these things. Now putting all these values in this equation, you will find that this product and this value will be 0 because they have a term containing the cross product of two identical vectors. So remaining terms can be written as x by I cross of j means k cap plus ax bz, but I cross of k equal to minus of j, so this is negative. Again this is ay bx, and j cross of I equal to minus of k, so this is negative, so ay bx k cap, this term is 0, this term plus ay bz, j cross k equal to I, and plus az bx k cross of I equal to j, and k cross of j is minus I, so therefore it is negative az by I. Now rearrange these terms, we will get a cross b. Rearrange these terms. At first we put together i's, x components, that means yes, this is I, so ay bz minus az by. Okay, then j, this is negative, so we put negative here, ax bz and this is positive az bx, but if we take out the common, then az bx, so this is negative now, plus ax by and ay bx. So in this way we can write the cross product of two vectors. But this method is very tedious. So we need to learn another method to calculate the product easily. In this case, here we put, since A equal to AXI plus AYJ plus AZK and B equal to BXI BYJ BZK. So here A cross B we write it in determinant form. So place the components in their respective below the respective unit vectors. That means you place AX below I and also the BX. Here the X component of A and it is the X component of B. Similarly AY BY AZ BZ. So if you want to calculate the I component, that is X component, that means I cap. So for calculating I cap, so we have to ignore this row and simply multiply this AYBZ and then putting the minus sign, then BYAZ. For J cap, look, for J cap we have to ignore this row and you need to put this row here. So rather than therefore the situation is very complex, but we can simplify this complexity by simply putting in negative term here, in negative sign, putting the negative sign here and right now J cap, and now maintaining the same orders. That means AX into BZ, AX into BZ and BX into AZ, BX into AZ. For K cap, similarly, here it is very easy for K cap because you have to ignore only this term. So for here AX into AY, AX into BY, sorry, minus AY AY BX. So in this way it is very easy to calculate. Look, the expression of this and this are similar. So in this way you can calculate vector cross product easily. So let's quickly revise what we have learned so far. In this lecture we have learned about the resolution of vectors, how we can express vector into its components in both in 2D and 3D ways, that means 2-dimensional and 3-dimensional space. Then we have learned the analytical method of vector addition and subtraction. After that we have learned about dot product and cross product in component forms. At this point I want to stop this lecture. If you like this content, then please like the video and also you can share the video. If you want more this kind of content, then subscribe the channel and don't forget to click the bell icon for latest notification. Thank you.